So let me start with saying that you don't need to you don't need to use every single piece of information that you are given to solve the structure. You almost are given 300% of information that is required to do it. You pick and choose whatever, you take the lowest hanging fruit first, and then you pick and choose what is really relevant and accessible. And then if that is not enough, you go deeper into more nuanced pieces of information. Okay, so in proton, carbon, NMR, and IR, what we have here is each of them has its strengths and weaknesses. Okay, sometimes the weakness is it just gives you a lot of detail, but you're free to ignore it. So let's actually start with IR spectrum, since this is the most accessible probably of all. So what do we see here?
So I think the 3000 is like a carbon-to-carbon bonds.
Mm-hmm. So we have some carbon hydrogen bonds. Okay, it's not entirely clear if it's beyond 3000 or not. Mm-hmm. So let's keep it more open view so far. So both sp2 and sp3 type of CH bonds. What we can tell that we have no OH, mm-hmm. Okay, and we have no carbon hydrogen bonds that are on alkynes, because that would show up at like 3300 and so on.
Mm-hmm.
Okay.
Do you see a large peak like right here?
And so this guy stands out. So if it's fair to say that it's about 1700 wave numbers, and these guys are usually very strong if it's a carbon oxygen double bond, a carbonyl of some sort.
Mm-hmm.
Okay, and I would stop here. Look for OH, look for carbonyls, and get a sense of what type of carbon hydrogen bonds you have. Okay.
Okay.
Let's actually go. What if I want it to stay? Okay, I'm still trying to figure it out. So let's erase this information so it doesn't follow us everywhere. Now I can't erase it even. Okay. There we go. Okay. Let's actually go back to the proton NMR, and I want to focus your attention on the formula. This is very useful information to have, because in NMR you always are giving information about number of hydrogens, and that's the integration that is given for the peaks. Okay. Mm-hmm. Most of the time you will just get numbers. Sometimes you will see those S-shaped lines. If the number is not given, you can kind of estimate the height between this point and that point, and then between that point and that point, and the ratio is about, in my eyes, about 2 to 3, and it happens to be the same ratio over here. So these numbers, although it's like 1.5 proton, you can have 1.5 proton. Mm-hmm. So these integrals were probably divided by a common denominator, which makes it 3H, 2H, and 2H, and 3H. So 5 total, 5, 2, and 3. Right. So what would be if I ask about chemical shift of these guys? What kind of protons are these? This is a very characteristic region.
Okay, so I know that the farther left they're more near the electric negative atom. And then I think at an 8, it's was carbonyl. I think you said would be.
Yeah, so if you have carbonyl that has hydrogens attached to it, they will show up much farther. The 7 between 7 and 9 are sometimes 6.5 to 9 is a region very characteristic for aromatic protons, and those aromatic protons are those phenyl rings and such. Okay.
Oh, okay.
Okay, so these guys show up very far. And what we know from integration is that we have 5 protons in that region, which, 99 times out of 100, it will tell you that you have mono-substituted phenyl ring.
Mm-hmm.
Yeah, so you just, out of 9 carbons and 10 hydrogens and oxygen, you just assigned 6 carbons and 5 hydrogens.
Mm-hmm.
Yeah. And without even looking at the splitting, okay, you have a blowout of a splitting here, and all you can tell about it is that it's quite complex.
Mm-hmm.
If you can try to read any information from it, and the information is there, but you're likely to just spin your wheels and waste cycles on that. It's better to move on to a more accessible piece of information, which are the other 2 peaks. Okay.
Mm-hmm.
So we have peak for 3 protons and peak for 2 protons.
Mm-hmm.
Which of them is shifted further?
That would be the 2 protons.
The 2. Okay, so we have 3 ppm, and it's a quartet. Okay, let me. It's a Q, which means how many
That would be
neighbors?
3 neighbors.
Okay, 3 neighbors. Here we have 3 protons and give a triplet. Okay, that means we have 2 neighbors.
So from what I can infer, it would be that this would be next to a methyl
Okay.
group, and then this is next to a CH2 bond.
Right, so that's an indicative of a fragment that is attached to something we don't know yet. CH2, CH3.
So a ethyl
Right, ethyl group.
group, yeah.
Additionally, this guy is shifted.
Mm-hmm.
Okay, because it has chemical shift of 3, so that would be closer to something electronegative.
Mm-hmm.
Okay, so how many carbons have we assigned?
That would be 2 plus 6, 8.
Okay, we know more.
Or
Okay.
Yeah.
If you remember from IR,
Mm-hmm.
we have this thing in our molecule.
Yes.
That's what we need left, is it?
Yeah, and so it looks like it goes in between the 2 fragments.
Right? So if you put an ethyl group on one side and a aromatic ring on the other,
Mm-hmm.
you got it. But I won't stop here.
Mm-hmm.
You need to look at the molecule now and try to predict what kind of spectrum you would predict for this molecule. Okay, so you would predict ethyl group CH3CH2,
Mm-hmm.
where the CH2 is shifted. Okay, we got it.
Mm-hmm.
And you would predict a aromatic ring.
And you would only shift the proton if it's inside of the electronegative molecule, right? So like it's within 3 bonds. So if the proton on it is within 3 bonds.
What you're talking about is splitting.
Splitting.
Splitting would always, you're right, it would be caused within 2 and 3 bonds. So when I want to highlight here, these protons are too far to be split by anything on this side of the molecule. These split each other, but they don't, in other words, see the other side of the molecule.
Okay.
Also, if you draw all the protons that you have in your aromatic ring,
Mm-hmm.
I'm going to color code them because the red ones are equivalent, the blue ones are equivalent, and the green one is
By itself.
by itself. So what we actually see in the NMR is a group of 2 and a group of 3, which makes sense because the 2 are closer to our carbonyl. Okay, so they are there is some shift happening, and they are a little bit farther, and the other 3 are farther, and they don't experience that shift that much, so they stay put right here. Okay, and that's it. We didn't even look at carbon spectrum. Okay, we didn't have to, but if once I figure out how this app works, and it doesn't shift with me, you can actually go back to the carbon spectrum, and what you would see this carbon will be distinctly shifted, and others too. What I want to just maybe add that in carbon spectrum for the ring, you would have 1, 2, 3, and 4 carbons. So the number of carbons that you have in a molecule will not match the number of carbons in the spectrum because you have some degree of symmetry.
Yeah.